Solving linear programming problems graphically. The goals for these lessons are to graph a feasible region given a set of constraints and then find the maximum value of an objective function given the constraints by graphing. A typical linear programming problem consists of finding an extreme value of a linear function subject to certain constraints. We are either trying to maximize or minimize the value of this linear function, such as to maximize profit, revenue, or minimize cost. For that reason, linear programming problems are classified as maximization, minimization, or just optimization problems. The functions that we are trying to optimize here is called an objective function, and the conditions that must be satisfied are called the constraints. Now, for example, let us consider the following maximization problem. We are given here this function that we are trying to maximize. So we are given c of xy, a function in two variables, x and y, which is equal to x plus 5y. We will try to maximize this subject to the following constraints. So these are the constraints: x minus y less than or equal to 5, and x plus 2y less than or equal to 6, and x and y greater than or equal to 0. Now, the set of all points satisfying the constraints is called the feasible region. And to get the feasible region, all you need to do is solve the system of linear inequalities here and get the overlapping region. So the set of all points that satisfies the system of linear inequalities here is the feasible region. So for instance, the 2 points 0, 0, and 2, 1 are 2 points which satisfies the constraints. Therefore, the 2 points are in the feasible region. You can verify that by plugging in each of these points to each of the inequalities here. For instance, if you plug into the first inequality here, the point 0, 0, you have 0 minus 0, that gives you 0, less than or equal to 5. Is that true? Is 0 less than 5? Yes. So therefore 0, 0 satisfies this first inequality here. Then you plug in again, or you evaluate again this inequality here by the point 0, 0. So let's see if that satisfies the inequality. So if x is 0, and then y is 0, this side of inequality is 0. So is 0 less than or equal to 6? Yes. So that means that 0, 0 is in the feasible region. And it is also on the region. When you say x and y greater than 0, that means the positive side of your x-axis and the positive side of your y-axis. That refers to the first quadrant. So is 0, 0 on the first quadrant? Yes. And it is actually the origin. And you have equalities here. So that's why it's on that feasible region. And then also 2, 1. Is 2, 1 on the first quadrant? Yes. So this third inequality here is satisfied. Then you just have to plug it in to this inequality here. Let's say, for instance, 2. If x is 2 and y is 1. So if x is 2, so you have 2 plus 2 times 1 is 2 times 1 is 2. So you have 2 plus 2, which is 4. Is 4 less than 6? Yes. So that is satisfied in this inequality here. Now for the first one, here we have 2, x is 2, and y is 1. So 2 minus 1 is 1. Is 1 less than or equal to 5? Yes, 1 is less than 5. So it is also satisfied in this inequality. So therefore, those 2 points are in the feasible region. So graphing the feasibility region of a particular linear programming problem makes solving the problem simple by way of this corner point theorem. The corner point theorem states that the maximum or the minimum value of the objective function always takes place at the vertices or the corners of the feasibility region. The other terminology for this corner point theorem is the fundamental theorem of linear programming. Let's consider an example here. Graph a feasible region given the set of constraints. Now, to graph the feasibility region, we first change all the inequality symbols here to equal signs. And in this case, we will then have lines. We have x plus 2y equals 6. We change this to equality. We have 3x plus y equals 12. This becomes x equals 0 or the y-axis, and this y greater than 0 is the line y equals 0 or the x-axis. Now we graph these lines. We graph each axis. So the line x plus 2y equals 6 is in blue, and the line 3x plus y equals 12 is in green. Now, first of all, we have x and y greater than or equal to 0. That means that we are going to consider the part of the graph of these two lines here on the first quadrant, because it is on the first quadrant where both these conditions are satisfied, when x and y are both greater than or equal to 0. So now the feasibility region is the region on this graph that meets all the requirements. We're just going to consider the part of the graph on the first quadrant, since we have set y, or in the constraint, x and y should be greater than or equal to 0. Now we can divide this into, on the first quadrant, you can divide that into 4 regions. You have this region here, that region 1, and then next is this region here, or this region here, or this region here. So we have 4 different regions. All you need to do to determine which of these 4 regions here is the feasibility region is to get a representative point. So you get a representative point, say for instance 1, 1. Okay, so you try 1, 1 here. Now, so if you try 1, 1, all you need to do is plug that in to the set of constraints, these 2 other constraints here. So if x is equal to 1 and y is equal to 1, you have 1 plus 2, which is 3. Is that less than 6? The answer is yes. So that is satisfied on this first inequality here. Then you go check on the second inequality. Plug in the point or the ordered pair 1, 1. So if x is equal to 1 here, you have 3 plus 1, that is 4. 4 is less than 12. So therefore, 1, 1 as our test point, which is on this region here, satisfies both of these linear inequalities here. So therefore, we say that this region here is the feasibility region. You can also pick another point to try and see if it is really on this. So pick another point on this graph here and see if really it is satisfies both of this inequality here. Or you can even pick a different point that is, for instance, in here. Let's say 4, 4. You try 4, 4 and see, so that is on this region here, and see if it satisfies the given inequality. So let's say, for instance, 4. If x is 4, you have 4 here plus 8 in here because you have 2 times 4. So 4 plus 8 is 12. Is that less than 6? No. So it's not satisfied on this inequality here. So therefore, this is not the feasible region. So hence, let's shade the feasible region here. This shaded region here is the feasible region in our example. Now let us consider another example here. We are to graph the feasible region subject to the following constraints. We begin by graphing the line 3x plus y equal to 50, and then the line x plus y x plus y is equal to 40. X plus y is equal to 40, and here the line x is equal to 0, or the y-axis, and this line y is equal to 0, or the x-axis. Now, since part of our constraint is that x and y are both to be greater than or equal to 0, that means we are only to consider the part of the graph on the first quadrant. So let's try to sketch the graph of these two lines here on the first quadrant. So to do that, we will first consider the line 3x plus y equals to 50, and then you get representative points on the first quadrant. Now we first get the x-intercept or the y-intercept. So let's say x is 0. When x is 0 here, or when x is 0 here, y is equal to 50. So y is equal to 50. And then another point on the line on the first quadrant, say for instance x is equal to 5. When x is equal to 5, plug it in here. You have 3 times 5, which is 15, and then you solve for x plus y, you solve for y. So 15, transpose that on the other side, y is equal to 35. So then let's have these 2 points here. So for instance, this is 50. This is 50. And then 35. So for instance, let's do increments of 5. So we have 5. So this is 45, 40, and then 35. So this is 35. And then we'll do increments of 5 here as well. So we have, in this case, we have this point here. So let us just, okay, so connect those 2 points. So this is the line 3x plus y equals 50. So we have x, then next we have x plus y is equal to 40. We do the same thing. We get representative points. So for instance here, this is x and y. When x is 0, y is 40. And then you can have a different point here. Say for instance, when x is 10, because we want to do increments of 5. So, but you can pick any number you want. But here you have, so for instance, if x is 10, y is 30. Y is 30. So then you plot those 2 points. So when x is 0, y is 40. So this is 40. I'll choose a different colored pen. So this is 40. And then the other point, when x is equal to 10, so for instance, this is 10, y is 30. So this one is, for instance, 30. This is 10, that one. Okay, so we will graph that line. So this is the line here. Now we want to see which of these is the feasible region. Now notice that this one looks like an intersection. You can verify that. You can verify to see which one is the intersection points of the given equations here. You can solve that by solving the system of linear equation, or you can even you suspect that the point 535 is an intersection point. You can do that by plugging or by evaluating x here equal to 5 and then solving for y. So if x is equal to 5, our y is equal to 35. So notice that 5, 35 are on both are on both equations, both linear equations. So therefore we say that the point 535 is the intersection point of the two lines here. Or you can also solve the two lines here using solving system of linear equations. But anyway, so this is the point here, that's the intersection. Now we want to determine which of these regions here is the feasible region. Again, the feasible region is the region that satisfies all the given inequalities here. So to do that, you can just get a representative point. So for instance, let's label this one. This would be my region 1, my region 2, my region 3, and region 4. I will know which one is the feasible region by getting a representative point. Say, for instance, I'll pick the point. So I know if I have x equals 1. Let's see if x is equal. Let's look at the point here. Say, for instance, x. So let you just have to pick a point, okay? So pick any point here. So like in this case here, suppose that would be the point 1, 1, 4. Okay, let's see if 1, 4 satisfies any of this equation here. So I have when x is equal, so you'll just have to evaluate. When x is equal to 1, when x is equal to 1, so you have 3 times 1, and then y is 4. And is that greater than or equal to 50? So you have 3 plus 4, that is 7. Is that greater than or equal to 50? The answer is no. So this one is not a feasible region. So we'll X that out. So that is not a feasible region. Now let's test whether region 1 is a feasible region. So to do that, let us first determine a representative point on region 1. So to do that, we can check on these points here. So this is the point, this is the y-intercept. That is the point 0, 50 coming from here. That's a y-intercept of this line here. And this red line here is this line here. And this is the x-intercept. So the x-intercept, this is the value of x when y is 0. So when y is 0, x is 40. So this one is 40, 0. So now we can pick a number. Maybe here, let's try to, maybe it would be easier. I mean, we're pretty sure when x, for instance, is 41. Let's just do that. When x is 41, so when x is 41, we want to know, so x is 41, we're sure that it is already on this side here. And then let's say, for instance, 41, 1. Is 41, 1? We know that 41, 1, or, well, let's see, let's have a bigger number, 41, 5. Okay, so let's consider the ordered pair 41, 5. Where is 41, 5? So 41, 5 probably on this point here. So that is 41, 5 as our test point. So let us consider the test point 41, 5. Now let's check if 41, 5 satisfies both of this inequality. Let's do that. When x is equal to 41, so we have 41 times 3 and then plus 5. Will you get a number that is greater than 50? So you know that 41 times 3 is 123. So you have 123 plus 5. That is greater than 50. 128 is greater than 50. So yes, it is satisfied on that inequality. Let's consider the second inequality. So for x, so x is 41. So 41 plus 5 is that greater than or equal to 40? 41 plus 5 is 48. Oh no, 46, sorry. 41 plus 5 is 46. So you have 46 is greater than or equal to 40. Again, that is also satisfied on this inequality here. So, therefore, we conclude that region 1 is our feasible region. So we have seen a point on region 1. We have seen a point on region 1 that satisfies both of our inequality. So therefore, this is our feasible region. If you aren't satisfied, you go ahead and pick a representative point on this region here. And you will see that one of the inequalities won't be satisfied. And this is only the points that lies on this region here will satisfy both of these inequalities. Now let us consider another example. Graph the feasible region subject to the following constraints. So these are all the constraints. We want to graph the region that satisfies all these given constraints here. We began by graphing the line x is equal to 8. So here we have x is equal to 8. And then the line here, x plus y is equal to 12. Here the line y equals 10. And these two lines here, this is the x is equal to 0 or the y-axis. And here y is equal to 0 or the x-axis. Now, since both of this x and y must be greater than or equal to 0, we're looking at the graph on the first quadrant. Okay, so now let's draw this. So we have this on so let's just draw this on the first quadrant. Then let's have x equals 8. So we have 1, 2, 3, 4, 5, 6, 7, 8. So that is the line x equals 8. We have equality here. So we use that line. So this is the line x is equal to 8. Then next we have the line y equals 10. So y equals 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So then the line y equals 10, let's choose a different colored pen. Let's say green. So we have this line here as y is equal to 10. Then let's now graph the line x plus y equals 12. So you can pick 2 points that satisfies that equation. So you can make it a table for x plus y equals 12. You can say when x is 0, y is 12. Here y is 12. And then when let's say when y is 0, x is also equal to 12. So we have these 2 points here. So we have 12, so 11, 12, so that point there. And then x is 12, so 8, 9, 10, 11, 12. So this point here. And then you just have to connect those 2 points. All right. So as you notice here, we have several regions. Okay, so we have, let's number our region. So we have this 1, 2, 3, 4, 5, 6, 7. Those will be the possible regions. Okay, those are the possible regions. Let me extend this one so we could easily see it. So this, I'll extend that, and I'll extend this line here. So there we go. So these are all the regions, and then we are going to get representative points there on our region to determine which one is the feasible region. Okay, let's try with region 1. Let's look at region 1. So for region 1, we know that the x values there should be greater than 8. So x is greater than 8 and y should be greater than 10. So you can have 9. So let's consider the point 9. And then the y should be greater than 10. So we can try 9, 11. 9, 11 and see if it satisfies all the inequality here. So for instance, x is less than 8. Oh, x is less than 8. X is equal to 9. 9 is not less than 8. So therefore, we say that this is not a feasible region. So let's X that out. That is not a feasible region because y is not less than 8. So let's just look for a region here that satisfies this. Because this one is easy to look at. So x must be less than 8. So it would either be 3, 2, 5, and 4. Those regions, 3, 2, 5, and 4. Okay, now also we have y must be less than 10. So therefore, we cannot pick 3 and 2 anymore because we know that for those regions, the y values are greater than 10. So therefore, we are just going to pick either between region 4 and region 5. So let's get a representative point for region 5. Okay, so for region or region 4. Let's choose region 4 here because it's easy. So let's consider the point 0, 0. You consider the point 0, 0 as your test point or the point 1, 1. Let's just do 1, 1. Let's do 1, 1. So when x is equal to 1, you have 1 less than 8. That's correct. So now when x is equal to 1 and y is equal to 1, you have 1 plus 1 here equals 2, and that is less than 12. So that is also correct. And 1 is less than 10. So therefore, here, this is a feasible region because it satisfies all the inequalities here. Okay, now just for the sake of curiosity, let's consider a point on region 5 and see if it's indeed not the feasible region. So here, let's look at this one. So this one, say for instance, we consider the points 1, 2, 3, 4. So 4 and then let's consider 9. So let us consider the point 4, 9. Is that in the feasible region? So if you look at this one, 4 is less than 8, correct. 9 is less than 10, correct. But 4 plus 9 is 13, and that is not less than 12. So this inequality here is not satisfied by 4, 9. So indeed, region 5 is not a feasible region. So we can go ahead and highlight this region here as our feasible region. This is the feasible region. Region 4 is the feasible region.